Now, since we're talking about sharing electrons in covalent bonds, we come to another important property of the elements. And this is known as electronegativity, and it becomes very important when we talk about covalent bonding. The best way to illustrate electronegativity is to ask a simple question. Do we think that the electrons are shared equally in this following molecule? So the electrons we're talking about are the electrons in the bond. Shared electrons between hydrogen and fluorine, are those electrons shared equally? And it turns out that they're not shared equally. Fluorine takes more than its fair share of those electrons. So the electrons spend more time around fluorine, and that leaves hydrogen kind of out in the cold, not having its fair share of electrons. And this results in a partial charge, partial being illustrated with this Greek symbol delta, where the element that takes more of the electrons, that hogs them, now because it has more than its fair share of the electrons, it has a partial negative charge. Whereas the element that's left in the lurch, it's now missing some of the time that it deserves with those electrons, and so it ends up with a partial positive charge on it. And this difference here comes from a term known as electronegativity, which is simply the ability of atoms to attract electrons to themselves, or the ability of an atom to attract electrons to itself. And every element in the periodic table has a different electronegativity. We can actually illustrate it nicely with a chart shown here. And what we'll notice is that there are some generally clear trends to electronegativity values. Electronegativity has no units, but as we go left to right across the periodic table, we see that the electronegativity increases, and it increases as we go up the table. Now, the direct reason for this actually gets back to chapter 7 with the effective nuclear charge. Remember that the effective nuclear charge increases as we go left to right across the periodic table. And thus the ability of an atom to attract electrons to itself is stronger as we have a stronger effective nuclear charge. And so then, and similar trends hold then for why the elements at the top of the periodic table have higher electronegativities than those at the bottom, since the electrons essentially were at much higher energy levels. We've gotten farther away from the nucleus as we go down the periodic table, and so the electronegativity decreases. From all of this, however, we can see that fluorine is the most electronegative, and remember that you might notice that the noble gases are left off of this. And that also has to do with the fact that the noble gases don't want any more electrons. They've got no desire to attract additional electrons to themselves, because those new electrons would have to go into an entirely new energy level. The noble gases are happy where they're at, so they're left off of this chart. And so fluorine is the most electronegative with an electronegativity value of 4. And then we've left off the F block metals, but you can see that cesium is one of the lowest electronegativity values at 0.7. So what falls out of all of this? Well, we have unfair sharing of electrons in bonds, and thus partial charges that result. And the reason for this is differences in electronegativity. We've got two different elements with different abilities to attract electrons to themselves. That difference is going to result in unfair sharing. But what results from the partial charges that we have in an unfairly shared bond is something known as a bond dipole. We refer to it as dipole because we can think of it as sort of the two poles of a magnet, or we have in this bond, we have a negative end of the bond, a partially negative, and we have a positive end. One element is partially negative, one element is partially positive, and we think of those as being two opposite poles. And so there's then quote, bond dipole. And we represent a bond dipole using an arrow here that shows, that is pointing towards the negative end of the bond dipole, and the other end of the dipole arrow has a plus sign, just illustrating that that end is the positive end of the dipole. A dipole itself is simply a separation of two charges of opposite signs, but does come from this term of two opposite poles. Now, there is also a dipole moment, which is given the Greek letter mu here, and this is simply the size and the directionality of the dipole. So it would essentially be just the magnitude of lumped in with the arrow shown above. We can actually calculate the magnitude of the bond dipole using this equation here, where E is the magnitude of the charge on either atom, and that magnitude of the charge, if we're simply looking at one single bond, in this case here, where we only have one bond between two elements, that magnitude of that charge is the same, the amount of positive charge on hydrogen is the same as the amount of negative charge on fluorine. Now, this is not necessarily true in cases where I have multiple atoms involved in a molecule, because I might have multiple bonds, and each of those bonds will have dipoles, and so the individual atoms may not have the same magnitude of charge. But if we look at the magnitude of charge on either atom in this case and multiply that by the distance between the charges, we can get to the magnitude of the bond dipole, which is known as the dipole moment. Now, we're not going to specifically in this class calculate any of those bond dipole moments, but we can make some generalizations from this. We can note that if the bond length is longer, given a certain magnitude of charge, that the dipole moment will be greater. Or if we have a shorter bond length, given the same magnitude of charges, that the dipole moment will be smaller. And you can look in your textbook and actually calculate some of the dipole moments for various molecules. We also can note that the dipole moment increases with increasing difference in electronegativity between the two elements. If the two elements have similar electronegativities, that is, similar abilities to attract electrons to themselves, then a bond between those two elements will result in a relatively fair sharing of electrons and small partial charges. However, if we have a large difference in those abilities, then the one that has a large ability is going to pull those electrons significantly away from the one that has a small ability, and we'll end up with a large then magnitude of charge on either atom. Now, a few examples here, just drawing out bond dipoles, is shown here. So carbon and nitrogen, I don't have to know the magnitude of the charge to be able to predict the direction of the bond dipole or which side gets the negative and positive. I can simply look at the periodic table and say that nitrogen is farther to the right than carbon, so it has a greater electronegativity. And so the bond dipole will be pointed towards the element with the greater electronegativity, because that's the element that will pull more of the electrons towards itself and be the negative end of the pole. Same thing with hydrogen and oxygen. And the overall point here is that every single bond will have a bond dipole. Every covalent bond will have a bond dipole and a dipole moment unless the two atoms that are bonded are identical. Otherwise, even if it's minute, there will be a difference in the electronegativity and thus bond dipole, even if it is a small bond dipole. So then here we can quickly go through and say, draw the bond dipoles for each of the following bonds. We've got a phosphorus-nitrogen bond, we've got bromine, chlorine, bromine, not chlorine, bromine and carbon, and we have a hydrogen and a boron bond. So what we can do is very quickly, phosphorus and nitrogen, those are both in the same column, and nitrogen is above that, above phosphorus. So I know, without having to look at the chart of values, I know that nitrogen will be more electronegative. So right off the bat, I can draw that bond dipole as pointing towards nitrogen. Now, bromine and carbon is a little trickier, because bromine is lower in the table, but it's farther to the right. than carbon. So I might want to look at the chart values to determine which of those is going to be more electronegative. So if I flip back to that chart really quickly, I notice that bromine has a value of 2.8, whereas carbon has only a value of 2.5. So if I were to draw between those two, bromine has a greater electronegativity than carbon, so I would draw it towards bromine. And one other thing while I'm here, I know I have a boron and a hydrogen bond. Looking here, I noticed that hydrogen is higher up in the table than boron, even though it's farther to the left. Hydrogen actually has a slightly greater electronegativity than boron. So hydrogen is the more electronegative element in this case. So in those two bonds, bromine is the more electronegative and hydrogen is the more electronegative. So if we flip back quickly to our problem here, we draw towards bromine and towards hydrogen. And that's simply how we would draw the bond dipoles for each of those bonds. Because we have unshared or unfairly shared electrons and we have bond dipoles, we can talk about a little bit slightly more quantitatively, we can talk about how unfairly shared those electrons are in a bond. And that gets us to something known as bond polarity. Now, bond polarity is simply a measure of how unequally shared those electrons are. And we designate bond polarity in three ways. We can have either a non-polar covalent bond, we can have a polar covalent bond, or we can actually just have an ionic bond. And those are our three measures for bond polarity. Now, what does that come from? Well, if the electronegativity difference is minor between the two elements, so somewhere between 0 and 0.5, if we take their electronegativity values and subtract one from the other, if that value is between 0 and 0.5, that's not a major difference in ability of the individual elements to attract electrons to themselves. And so the electrons are going to be fairly evenly shared in the bond, and we refer to that simply as a non-polar bond, and a non-polar covalent bond. Now, if the difference is large between 0.5 and 2, we would refer to that as being a polar covalent bond. Polar simply means there is a decent size, there's a large dipole moment, the electrons are unequally shared, but it's a covalent bond. They are shared, but pretty unequally. So I'm going to have a sizable partial negative charge on one element, sizable partial positive charge on the other. Now, if the electronegativity difference is extreme, so greater than 2 generally, we actually now start to treat that not as being electron shared, but we say that one element so strongly pulls, the difference between their abilities to attract electrons to themselves is so great that one element effectively just takes the electrons entirely to itself and leaves the other electrons with essentially no electrons around it from that bond. And it becomes no longer a shared bond, but an ionic bond. And so if we have greater than 2, then we do treat that as being an ionic bond. Now this leads to some complications because there can be cases where we have a difference greater than 2 for cases where we may not have a metal with a non-metal. We think about ionic bonds as being only metal with non-metal. However, there are a few rare cases where I can have non-metals where the difference is so great that we actually begin to treat it as an ionic bond, and it has some measure of ionic character to it. A few examples here just to go through. So carbon and hydrogen bond in CH4. If I look at those electronegativity values and simply take the difference, carbon is 2.5, hydrogen is 2.1. So that difference is 0.4. That's a fairly equal sharing. That's a non-polar bond. And it would certainly be a covalent bond. Non-metals here are involved. CO, that bond in methanol, for example, well, that's a little bit different. Carbon's still 2.5, oxygen is 3.5, so that difference is 1.0. That is now a polar bond. Oxygen is quite a bit more electronegative than carbon, and so it pulls quite a bit more than its fair share of electrons towards itself, and thus we end up with a polar bond. We have a sizable partial negative charge on oxygen, sizable partial positive charge on carbon. And then finally, if we looked at the bond between oxygen and sodium, for example, well, we would think already, based on our metal, non-metal, that this would be an ionic bond, but we can confirm that simply by looking at their electronegativities. Oxygen's 3.5, sodium 0.9, so we have a difference of 2.6. This is definitely an ionic bond here. Oxygen fully takes the electrons away from sodium. And that's how we use this designation of bond polarity and electronegativity to talk about how atoms share electrons and form bonds, or don't share electrons in some cases, how we get chemical bonds that we then rely on for reactions and life.